The cellular telephone is a major part of the ongoing telecommunications revolution. The ubiquity of this device has changed our lives in profound ways. And for this reason alone, we should know something about the underlying technology. I'm sorry. But cellular technology is also worth knowing about because it's often more problematic than the other technologies in our lives. Why do I get good service in some areas and bad service in others? Why do I sometimes lose my connection for no apparent reason? Why does my battery consumption seem to vary so wildly? Why did they build that ugly antenna tower in my backyard? Well, as you know, I'm a strong advocate for being an informed user of technology. Today, I hope you'll come to recognize that being an informed user of cellular technology can be particularly beneficial. At the most fundamental level, cellular communication involves analog or digital encoding of a radio carrier signal. Thus, we can't understand the technology without first understanding radio. Anytime electrons move at varying speed, they generate electromagnetic radiation that propagates through space at the speed of light. We've seen this phenomenon before. The reason twisted copper wires are twisted is to reduce the adverse effects of electromagnetic radiation emanating from the wires as current flows through them. Coaxial cable uses a metal shield to contain the electromagnetic field within the cable and to protect against electromagnetic interference from outside. Because electromagnetic radiation oscillates as it propagates through space, it's characterized as a wave phenomenon. And like any wave phenomenon, it can be classified according to its frequency. The electromagnetic spectrum, with its associated frequencies, is illustrated here. At the bottom end is low-frequency, long-wave radio. The progressively higher frequencies are conventional radio, including the frequency bands used for AM and FM radio, then microwave, infrared, visible light, ultraviolet light, X-rays, and gamma rays. By the way, these low-frequency radio waves are called long waves because the physical length of a wave is inversely proportional to its frequency. The 30 Hertz radio waves used by the US Navy to communicate with submarines are over 6,200 miles long. FM radio waves, transmitted at 100 megahertz on your FM dial, are about 10 feet long. Microwaves at 10 gigahertz are about 1/100th of an inch long, so small that they can be scattered by raindrops, which explains why microwave communication signals can be degraded by rain and fog. In general, electromagnetic waves with low frequency can travel much farther than those on the opposite end of the spectrum, but they have significantly lower capacity for carrying information. Electromagnetic waves with high frequency have far greater capacity by virtue of their greater bandwidth, but they also attenuate more quickly. And as we've seen with microwaves, their waveforms are so small that they're highly susceptible to atmospheric interference. For these reasons, most wireless communications use the middle of the electromagnetic spectrum. Mobile phones generally operate primarily in the frequency band just above FM radio, from about 700 to 2,500 megahertz. So, how does radio communication work? Well, in general terms, a transmitter generates an alternating current that's been modulated or electronically mixed with a signal representing the information that's being transmitted. This alternating current is passed through an electrical conductor called an antenna. And because the current is oscillating, it generates electromagnetic waves at the same frequency as the current. These waves radiate off the antenna into space at the speed of light. As long as the frequency of the alternating current is in the radio frequency range, the resulting electromagnetic waves will be radio waves. At the other end of the transmission, the process happens in reverse. The electromagnetic waves impinge upon the receiving antenna, introducing a corresponding electrical current. This signal can then be demodulated to retrieve the transmitted information. Now, antennas can be designed to transmit and receive in all directions, like this one on my walkie-talkie. Or they can be designed to focus electromagnetic waves in a particular direction, as we saw with the directional antennas used on microwave relay stations last lecture, and as we'll see with parabolic satellite dishes in the next lecture. And so we come to the cell phone, which is really just a radio transmitter receiver. In this sense, the cell phone isn't really new technology. It's not fundamentally different from those walkie-talkies we see in the World War II movies, with two exceptions. First, a walkie-talkie typically operates on only one radio frequency, so you can either transmit or receive at any given time, but not both. Most cell phones operate on two frequencies to facilitate simultaneous transmission and reception, called full duplex communication. Now, I say most because a recent technological innovation actually allows simultaneous two-way communication on a single frequency, as we'll see later in this lecture. Second, those original walkie-talkies were all analog devices. And while the first generation of cell phones was analog as well, all modern mobile devices encode and transmit information digitally. Although the cell phone itself is conceptually similar to a simple walkie-talkie, what makes cellular networks so complex is the need to handle millions of conversations simultaneously. The electromagnetic spectrum is a finite resource. If we start handing out 2 frequencies per mobile phone, we'll run out of frequencies long before we run out of mobile phone users. Cellular networks handle this challenge through a concept called space division multiplexing. A geographic region is subdivided into a regular grid of smaller areas called cells. And yes, that's why it's called a cellular system. Each cell has its own antenna and base station. Taking a hint from nature, these cells are normally hexagonal, like the cells of a honeycomb, to provide efficient coverage with minimal overlap. Within each cell is a base station, which incorporates the radio transmitters, receivers, and antennas that communicate with all mobile devices located within the cell. The power of the radio transmitter is deliberately limited so that frequencies can be reused in other cells without causing interference between transmissions. But which other cells? The answer to that question depends on a factor called the cellular reuse pattern. The first generation of commercial cellular technology was launched in Japan in 1979 and called 1G for first generation. In this system, each cell was about 8 miles wide, and the cellular reuse pattern was 7, meaning that each cell of this 7-cell module used a completely different set of frequencies. Now, when we replicate this reuse pattern across the countryside, we see that it always provides a buffer of 2 cells between any pair of cells using the same frequencies. For example, any 2 yellow cells have 2 non-yellow cells between them in any direction. Now, the electromagnetic spectrum is a highly constrained resource, and so it's tightly controlled by government regulatory agencies like the U.S. Federal Communications Commission. In 1G networks, the FCC typically allocated enough radio spectrum to provide each service provider with 832 voice channels. That is, 832 discrete frequencies that could handle simultaneous voice communications without interference. 832 channels allow for half as many two-way conversations, or 416. With a cellular reuse pattern of 7, these channels had to be allocated equally among the 7 cells in each module. As a result, each of those 8-mile diameter cells in the 1G system could serve 416 divided by 7 equals 60 simultaneous conversations. Accommodating 60 phones within an 8-mile diameter was a revolutionary capability back in the 1980s. Today, it probably wouldn't even be good enough to qualify as inadequate. And so, the history of cellular technology development since then has revolved around the need to handle an ever-increasing number of users, demanding ever more bandwidth for both voice and data communications, and ever more reliable and responsive service. One response to these challenges has been simply to use more efficient cellular reuse patterns. For example, this one is based on a 4-cell module, which still provides a buffer of 1 cell between each pair of cells operating on the same frequencies. This simple change allows for the use of 75% more frequencies per cell, with a corresponding increase in the number of users. However, the smaller buffer between the common frequencies also requires the use of antennas with more precise control of their coverage areas to minimize the likelihood of interference. One common technique for achieving better coverage has been to place the antennas not at the center of each cell, but rather at 3 of the corners, like this. With this configuration, directional antennas are now used to limit each tower's coverage more effectively to the assigned cell. Note also that in this configuration, each cell is served by 3 different towers, providing more uniform coverage, and each tower covers 3 different cells. And that's why, at the top of most cell towers, you'll find triangular arrays of directional antennas like this one. Each side of the triangle is covering a different cell. And viewed from a different angle, we can see that each antenna is angled slightly downward here to ensure that transmissions don't overshoot the cell and cause interference. Another response to the need for greater capacity has been to use smaller cells in areas where larger numbers of users are congregated. The capability to subdivide big cells into little ones like this was an important new feature of the 2nd-generation cellular network standard, or 2G, which was first deployed in 1991 in Finland. Since then, we've seen the establishment of microcells, each about a mile wide, picocells, typically 500 feet or less, and even femtocells on the order of 30 feet. Now, picocells and femtocells are often used to extend cell coverage indoors, the former for office buildings, shopping malls, train stations, and similar large public facilities, the latter for small businesses and even individual homes. Beyond the improved coverage, smaller cells also have the advantage of requiring less power at the base station and in your phone. And yes, today, most cell phones do have variable power output, and the cellular base station actually controls your phone's power level to maintain an adequate signal while minimizing drain on your battery. But this relentless subdivision of cells has some significant downsides too. Obviously, one is the added cost of more antennas, more base stations, and more network interconnections. Evidently, this cost is being met by the ever greater number of subscribers that these smaller cells are serving. So perhaps it's not a significant issue. But a much more significant drawback of smaller cells is a larger number of handoffs, which occur every time a user moves from one cell to another. We'll talk about how handoffs work shortly. For now, it's only important to recognize that the handoff is a complex process requiring considerable computation and information exchange between your phone and the cellular network. Consequently, demanding too many handoffs in too short a period of time can cause problems. Often this challenge is addressed by using macro cells, sometimes as large as 20 miles across, in rural areas and along highways where users are most likely to be crossing from cell to cell at higher speeds, and by using smaller cells in areas where people are likely to remain in one cell for relatively longer periods of time, like shopping malls and office buildings. But what happens when a highway runs right through the middle of a densely populated metropolitan area like this? In such situations, many modern cellular networks use umbrella cells, which provide redundant wide area coverage overlaid onto a grid of smaller cells. In this arrangement, when a microcell detects a mobile device moving at very high speed, it hands off the call to the umbrella cell, thus significantly reducing the subsequent number of handoffs. Allowing the use of variable cell sizes contributes significantly to enhanced capacity in 2nd generation or 2G cellular networks. But the most important contributor by far was the change from analog encoding in 1G to digital encoding in 2G. This change allowed for the encryption of voice transmissions, addressing a particularly serious security concern with wireless communications, and it opened the door to the transmission of data as well as voice. Text messaging, officially the Short Message Service or SMS, was an integral part of the 2G standard, and it paved the way for the smartphones of today. But most importantly, the switch from analog to digital allowed for significantly more efficient use of the limited electromagnetic spectrum assigned to cellular communications because it incorporated multiplexing, or to be more precise, it incorporated more sophisticated forms of multiple access. So what's the difference between multiplexing and multiple access? In 1G networks, the simple system of allocating two frequencies to each user is called frequency division multiple access. The concept is quite similar to frequency division multiplexing, which we discussed last lecture in the context of wired networks. But there's a subtle difference. In multiplexing, multiple conversations are combined into a single signal for transmission through a wire. In a wireless network, the individual conversations are transmitted independently between various mobile devices and the cellular base station. This is multiple access. The major technological advance in 2G networks was a new system called time division multiple access, which actually combines the concepts of frequency division and time division multiplexing. In time division multiple access, the entire available frequency spectrum is first subdivided into channels, as was done with frequency division multiple access. And then, within each channel, as many as 8 different phones are each assigned a specific time slot for transmission. The phones then transmit in short bursts within their respective time slots in rapid succession. Each cycle of 8 transmissions is so short that users perceive their conversations as continuous, even though they're actually a series of discrete samples. Now, by itself, time division multiple access provides an 8-fold increase in capacity over the simpler frequency division system used in 1G networks. But with increased capacity comes a significant new technological challenge: synchronizing transmissions by mobile devices located at different distances from the cellular antenna. Even though radio waves propagate through space at the speed of light, the time slots allocated to each burst of data are so small that the time it takes a transmission to travel across a cell can actually cause a given burst to miss its assigned time slot. To compensate for this travel time, the base station calculates something called a timing advance for each phone and sends that information to the device. The phone then sends its bursts of information just a little bit earlier by the amount of the timing advance, so they arrive at the antenna at precisely the correct moment. This system works well when the phone is standing still. But when the phone is in motion, there's typically some lag in matching the timing advance to the phone's actual position. Thus, to prevent interference, a small chunk of time needs to be inserted between the assigned time slots in the transmission sequence just to provide margin for error. And this added time robs some of the efficiency gain through time division multiple access. Now, this limitation has been very effectively addressed in third generation or 3G wireless networks, which were first deployed in 2001. Most 3G networks accommodate multiple users through a fundamentally different approach called code division multiple access, also called spread spectrum. In this system, there's no subdivision of the available spectrum into smaller frequency bands. Rather, all users within a given cell are communicating across the full spectrum at the same time. In this system, your mobile device modulates its original signal with a unique, randomly generated code that's provided by the base station. During this process, the bandwidth of the transmission is effectively spread across the full available spectrum, but it's done with a unique pattern that can be recognized and decoded by the receiver. Now, code division multiple access is very difficult to visualize, so let's try a simple analogy. Have you ever been in a foreign country, in a public place where lots of people are talking simultaneously in a language you don't understand? All you hear is a cacophony of unintelligible sounds. And then suddenly, you hear a single voice speaking in your own language. And as soon as you discern the unique and familiar pattern of speech in your own language, you're able to lock in on that single voice and filter out the undecipherable cacophony of the other voices in the room. This is the essence of code division multiple access. And in a cell network, this system uses electronic spectrum 10 to 20 times more efficiently than the simple frequency division scheme used in 1G networks. It also produces further increases in capacity by reducing the cellular reuse pattern to 1. In other words, the code division multiple access system allows for adjacent cells to operate on exactly the same frequencies without interference, as long as these adjacent cells use different codes. This feature represents another 7-fold increase in the number of users per cell in comparison with the reuse pattern of the 1G network. The efficiencies gained from this system arrived just in time to accommodate the explosion in demand for mobile connectivity that accompanied the introduction of the iPhone in 2007. But demand has only increased since then, as consumers have increasingly come to rely on their mobile devices for such functions as internet access, streaming video, gaming, voice over IP, mobile television, video conferencing, and cloud computing. To address these demands, enhanced 3G and recently introduced 4G systems have incorporated such features as advanced antennas that can transmit multiple parallel data streams simultaneously, data compression to pack more information more efficiently into a communications channel, duplexing techniques which allow a single channel to share both the outgoing and incoming halves of a conversation, and new schemes for multiple access that, I must admit, are essentially indistinguishable from magic. All of these changes require an extraordinary level of coordination between the research and development community, government regulators, standards organizations, both domestic and international, wireless carriers, and hardware and software developers. And this challenge can only ever be met temporarily because demand is ever increasing and new technological paradigms are constantly emerging. The 5G standard is due out in 2020. Watch for it. It's hard to imagine a more dynamic and unpredictable context for technological development. Well, up to this point, we've discussed the radio communication link between your mobile device and the nearest cellular base station. But this is really only the tip of the iceberg. The base stations are just intermediate nodes in a far more extensive network of networks, illustrated here. Tens or even hundreds of base stations are connected to devices called base station controllers, which in turn are tied together by regional facilities called mobile switching centers. And by the way, the links between these base stations and controllers are usually landlines, but occasionally microwave links, as is the case with this particular station. The mobile switching center operates like a local exchange in the public switch telephone network. And indeed, it also provides the interface between the cellular network and the PSTN. The mobile switching center sets up and releases end-to-end calls, both mobile to mobile and mobile to PSTN. As the diagram indicates, base station controllers are also connected to the general packet radio service, a packet switched network that's overlaid on top of the circuit switched phone network and handles all internet data packets passing between your mobile device and the internet. Another critically important function that's performed jointly by the base station controllers and the mobile switching centers is the handoff of calls from cell to cell. Here's how this process works. Anytime you turn on your phone, it tunes into a specially designated frequency called the control channel, and it listens for something called a system identification number, which is broadcast by each base station to identify the associated cellular service provider. If your phone can't find a system identification number, it displays that annoying no service message. Your device knows the system identification number of its own service provider. So if it detects this number being broadcast, it knows it's operating within the coverage area of its own provider. If not, it's roaming within a different provider's area. On the same control channel, the phone then identifies itself to the service provider, and the mobile switching center stores the phone's location in a database. Through this mechanism, the system knows where your phone is located whenever it's switched on, so the associated mobile switching center can find you when someone dials your number. Now, when a call does come in, Your switching center looks up your location in the database and then communicates with your phone over the control channel, sending you a ring signal and all the necessary coordinating information to complete the connection. For example, in a time division multiple access system, it provides the two frequencies and the time slots for transmission. In code division multiple access, it provides the code. When you answer the phone, you've got an end-to-end connection to the person who's calling you. Now, let's say that you're driving while the call is in progress. The base stations covering your cell are constantly monitoring the quality of your signal as measured by the signal strength, error rate, voice quality, and other metrics. When these measurements indicate that you're approaching the edge of your current cell, the base station controller, or in some cases the mobile switching center, coordinates with the adjoining cell, called the target cell, to effect a handoff. At the appropriate moment, your phone receives a signal on the control channel telling it to change frequencies, or in a code division multiple access system, to start using a new code. Once the switch is made, control of your call transfers to the target cell. In some systems, this changeover happens instantaneously. In others, there's a short period in which you remain connected to both cells and your phone can choose the stronger signal. In either case, the handoff is usually so precisely controlled that it can occur in the middle of a word and you won't notice it. But calls do occasionally get dropped during handoffs. When this happens, the most common reason is that the target cell doesn't have an open channel to give you. Now, in many ways, cellular communication is indicative of our love-hate relationship with technology. Even as we demand better coverage, better speed, and more wireless services, we staunchly oppose the construction of that ugly antenna tower in our neighborhood or on that picturesque hilltop out in the countryside. But not in my backyard really doesn't work very well with cellular networks. Coverage requires proximity to an antenna. And once the geometric grid is established, the corner of a cell falls where it falls. The cellular provider just doesn't have that much flexibility to move it around. Now, granted, competing service providers often exacerbate this problem by establishing their own independent systems of antennas. Thus, it's not unusual to see two cell towers standing on top of the same hilltop, like this. Fortunately, the level of conflict over this issue does seem to have abated somewhat within the past few years. These days, there seems to be less opposition to the construction of towers, perhaps because they've become so ubiquitous that we hardly even notice them anymore. And the service providers have done their part in exercising more creativity in the design and placement of their antennas. Consider just a few examples. It's now quite common to see cellular antennas grafted onto water towers and power transmission towers. Now, these installations are certainly no less ugly than standalone towers, but they are effective in concentrating ugliness in one location so that some other location might be spared. Particularly with the advent of microcells and picocells, it's now common to see cell antennas placed on the roofs of commercial buildings rather than on standalone towers. And in rural areas, well, you've got to love the antenna disguised as a stately pine tree, and in tropical climates, as a palm tree. These cellular cacti aren't terribly convincing, but they're a noble effort nonetheless. And here's my personal favorite. On the steeple of this beautiful old church in Poland, this antenna is perfectly disguised with trompe-l'oeil brickwork. Now that's an accommodation between aesthetics and technological necessity to which we can all aspire. Next lecture, we'll take wireless communications to a higher level with satellite communications.